Alzheimer's disease doesn't begin when it's diagnosed. It begins silently decades before when a single memory fades. And by the time we see the symptoms, it's often too late to turn back the clock. But what if we could see the future? What if we could intercept this disease way before it showed its face? That is the mission that I took on, and this is my story of how I made an AI powered diagnostic system that does exactly that. My research introduces a non invasive framework that uses artificial intelligence to forecast the onset of Alzheimer's disease up to 24 months before clinical symptoms appear. With a 92.4% sensitivity and 91.4% accuracy, it helps us to reimagine early detection in a more scalable, explainable, and accessible way. Starting from the literature review, existing models have paved their way from classical machine learning like SVMs and random forest to deep neural networks and attention mechanisms. Yet three issues keep surfacing. Number one, they detect Alzheimer's too late, often after brain damage has already occurred. Number two, they rely heavily on invasive procedures like lumbar punctures. And number three, they're often black boxes offering predictions without transparency. I wanted to change that, so I built a hybrid framework that goes deeper, earlier, and more transparently. My methodology consisted of 4 steps, with data sourcing being the very first step. I started by accessing two of the most extensive, globally recognized datasets in Alzheimer's research, ADNI and OASIS-3. ADNI, Alzheimer's Disease Neuroimaging Initiative, with over 10,000 MRI and biomarker samples, and OASIS-3, which are used for validation and external testing. Step 2 was pre-processing and balancing of the data. I applied Z-score normalization and feature scaling, and to address class imbalance, particularly unrepresented MCI cases, I use SMOTE, synthetic minority oversampling technique. The step 3 was the model design. I created a hybrid ensemble architecture. It was a DenseNet 1-to-1 CNN to extract hierarchical features from brain MRI scan, and a gradient boosting machine to analyze structured data like A beta 42/TAU ratios and blood proteomic profiles. You may ask why DenseNet 1-to-1? It's efficient, deep, and excels at capturing subtle spatial patterns, ideal for identifying hippocampal atrophy at early pre-symptomatic stages. Why did I use GBM? It's powerful in tabular data and interpretable, allowing us to understand which biomarkers contribute to prediction. To prevent overfitting, I integrated dropout layers for dimensionality reduction and feature selection. I applied recursive feature elimination and principal component analysis. The step 4 was model training and validation. The dataset was split into 70-30 for training and testing. I used tenfold cross-validation for robustness. Evaluation metrics included accuracy, precision, recall, F1 score, and AUC. The results surpassed every benchmark with an AUC of 0.942, accuracy of 91.4%, recall of 90.8%, and sensitivity in MCI detection of 93.8%, which is 2 years before clinical symptoms. Compare that to MRI-only models, which has an AUC of 0.869, or blood-only models, which has an AUC of 0.791. The hybrid approach didn't just improve performance, it redefined what was previously possible. This model goes beyond prevention. It empowers clinicians to act early, before memory loss and before decline. It allows for early enrollment in clinical trials, tailored therapies, and possibly one day true prevention. And crucially, it's non-invasive, explainable, and built for scalability. It doesn't just work in a lab, but it has the potential to work in the real world.